Very good. So before we begin, I need to put this here. Okay. So welcome to the mathematical methods for physics class. It's going to be a very long journey in this mathematics. 8 weeks total, and I hope that you enjoyed the discussion in this class. And the reason I am talking in English is that because we have students from Bhutan that is studying with us. But we also have many Thai students listening to the lecture. So I will switch back and forth between the Thai and the English. And I hope I can make it balance as not to disrupt the material in this class so much. ผมก็จะพยายามพูดสลับไปมาระหว่างเนื้อหาที่เป็นไทยกับภาษาอังกฤษนะครับก็หวังว่าจะได้ประมาณสัก70 ก็จะเป็นภาษาอังกฤษแล้วก็30เป็นภาษาไทยนะครับก็หวังว่าคงจะสามารถที่จะตามเนื้อหากันได้นะครับเนื้อหาในวิชานี้นะครับที่ผมเตรียมมานั้นส่วนใหญ่ก็จะเป็นวิชวลนะครับก็คือว่าคุณสามารถที่จะดู PowerPoint หรือว่าสไลด์ไปได้คล้ายๆกับการดูหนังaction movie นะครับเพราะว่ามันจะไม่มี dialogue มากพอสมควรนะครับก็พอจะฟังเข้าใจได้นะครับ so we have 3 students from Naresuan University, and I hope that you ask a lot of questions. Or maybe I expect you to ask maybe 5 questions per lecture, and that's because if you have a question, it is likely that other students will have the same question that you do. So if you ask, it'll be very beneficial to other students as well. สำหรับผู้ที่มาฟังเลคเชอร์นะครับถ้าอยากจะถามคำถามสามารถที่จะอินเตอร์รัปหรือว่าถามผมได้ตลอดเวลานะครับเราจะได้มีฟีดแบ็กเรียกว่าการตัดบทสนทนาให้ไม่ไปเร็วไปช้ามากเกินไปนะครับเวลาถามเป็นไทยก็ได้นะครับไม่ต้องเป็นภาษาอังกฤษนะครับผมอาจจะแปลให้เป็นภาษาไทยนะครับให้Mrs. D. Chen นะครับได้ฟังอีกครั้งหนึ่งนะครับเพราะฉะนั้นการถามทำให้ผมทราบว่าบางทีผมไปเร็วไปช้าเกินไปถ้าเกิดผมพูดภาษาอังกฤษมากเกินไปพูดไทยน้อยไปก็บอกได้นะครับบอกได้ตลอดเวลานะครับตอนนี้มีเท่าที่ผมเห็นตรงนี้มีผู้ร่วมรายการทั้งหมดนะครับ13 คนนะครับรวมทั้ง Miss Dichen Chanidapa and who I believe this person greeted me in the beginning Patharada นะครับ okay so let's get to the lecture that we have today. Okay let me switch to the PowerPoint presentation in this here. Okay first go to control and then PowerPoint presentation. There you go. So we have this. The format of this lecture, I am going to use both the PowerPoint presentation and sometimes when you want to derive certain thing, I'm going to use the iPad screen as I'm showing you here. Also, I can see the Microsoft Teams as well in this small box screen. And I hope if you have any question, please open microphone and turn on the microphone and then use your voice because otherwise I couldn't see what is being popped up on the screen. Okay, so let's go to the material for this lecture. Okay, we have 8 topics that I am going to cover in 8 weeks. Let's look at the resources first. What you need to survive this course. มาดูแหล่งรวบรวมความรู้ต่างๆนะครับที่เราจะใช้ในการเรียนวิชานี้นะครับ First, this is the instructor. My name is Teepanis Chachiyo, and I'll be your instructor today. And the textbook that we are using was written by Krasik. Okay, that's the author. I chose this book because it is very comprehensive. The writing is not very good.ผมไม่ชอบสไตล์การเขียนเท่าไหร่นะครับแต่ว่าด้วยความที่มันมีความสมบูรณ์ของเนื้อหาทุกๆอย่างในตัวมันเองประมาณ1,200หน้ากระดาษนะครับเพราะฉะนั้นเนี่ยถ้าเราเรียนเล่มนี้แล้วก็คุ้นกับการลำดับเนื้อหานะครับในอนาคตเนี่ยจะสามารถกลับมาใช้เป็นอ้างอิงได้สะดวกนะครับได้สมบูรณ์พอสมควรนะครับ So the lecture that we are going to be using here, it will be in Microsoft Teams. And if you miss any of the lecture, you can always come back at night and review, watch the video online later. I don't give you the notes because I want you to take your own notes. So you should, of course, you have the video, so you can always come back and take the good notes from the video. For those that are actually enrolling in this course, the NU students, you can access the online NU e-learning. And some of the material in this class is going to be Python and code. So we will use what is called Google collaborations, which I'll show you how to do that later on. Okay. เราจะใช้บางทีถ้ามีการเขียนโปรแกรมคอมพิวเตอร์นะครับเราก็จะใช้โปรแกรม Python นะครับแต่ว่าคนที่ไม่สามารถเขียนโปรแกรม Python ได้ก็ไม่ต้องกังวลนะครับเพราะว่าผมมีตัวโค้ดให้สมบูรณ์นะครับเพียงแต่ว่าเรามีหน้าที่มาแก้ไขเล็กๆน้อยๆนะครับในการทำโจทย์ทำกันบ้านแค่นั้นเองนะครับเดี๋ยวจะคุยกันเรื่องของการใช้ตัว Python แล้วก็บวกกับที่เรียกว่าเป็น Google Collab เนี่ยอีกสักครั้งหนึ่งนะครับ So before we go to the overview that show the all the material in this class, let me give you a one-stop website so you can always go to this website and have access to all of the material that I have just talked about. มาดูตัว OneStop เว็บไซต์นะครับที่คุณจะสามารถไปที่เดียวแล้วก็สามารถจะไปโหลดเอาข้อมูลต่างๆที่บอกมาเมื่อกี้นี้นะครับได้ในคราวเดียวนะครับเดี๋ยวต้องไปที่ในส่วนของเว็บ Google Chrome สักนิดหนึ่งนะครับนี่ Chrome Scenes แล้วก็ไปที่ Chrome โอเคนะครับถ้าเกิดว่าอันนี้คือต้องการจะเสิร์ชหาเว็บนี้นะครับมันชื่อว่าเว็บสยามฟิสิกส์นะครับเดี๋ยวผมขออนุญาตขยายขนาดของสกรีนให้ชัดนิดหนึ่งนะครับก็พิมพ์คำว่าสยามฟิสิกส์นะครับใน Google Search มันน่าจะมีอยู่ที่ตัวแรกนะครับตรงนี้นะครับซึ่งพอคุณเข้าไปเนี่ยคุณก็จะเห็นเป็นเว็บไซต์นะครับที่จริงๆแล้วมีเนื้อหาอยู่เยอะพอสมควรนะครับที่คุณสามารถเข้ามาดูตรงนี้นะครับ so this is what we call the Siam Physics website and you can access that using the Siam Physics keyword on Google. I will take you to this website and you can look at these online courses on the left panel. And in here, you will notice that we have this mathematical method for physics. The mouse is pointing in this icon. You click there. Oh, okay. So now it is showing here all the resources, the Microsoft Teams link that will take you here into this lecture and all the Google collaboration file and so forth. Okay. So that's how you access the OneStop website. Let me go back to the PowerPoint and the overview of the material in this course. We change to PowerPoint scene and then the what else? Let's go to the PowerPoint screen. Okay, here we have it. Okay, so I have divided the 8 weeks of material into 3 groups. The first one is called the expansion. Of course, it's going to be very important as the basic of all the rest of the material. expansion ก็เป็นไอเดียที่จะต้องเป็นพื้นฐานของการเรียนทุกๆสัปดาห์ที่จะตามมาในอนาคตนะครับ and the highlights the climax of this expansion chapter will be the applications of Fourier transform and the introduction, I think, of how you can use Python and Google collaboration code and platform for your research. สำหรับคนที่เป็นนักการศึกษาแล้วก็เป็นคุณครูอาจจะได้ประโยชน์มากสำหรับการดูตัวอย่างการนำเสนอเรื่องของ Fourier expansion นะครับแล้วก็การนำเอาตัว Google Collab platform แล้วก็ Python เนี่ยมาบวกกันเพื่อจะใช้เป็นสื่อการสอนนะครับในการนำเสนองานต่างๆ and the next group of the material is called Numerical and so we'll look at many topics under the numerical umbrella. The climax of this will be, for example, we are actually going to learn how to solve diffusion equation and make very fancy visualizations. Okay, in this case, what you're seeing here is how the gas molecules initially on the left of the box diffuses to the right and then eventually equilibrate the entire system. So we are going to solve this equation using computer and numerical method. Okay, and also the highlights of this chapter is that you are going to learn how to solve Newton's equation, and not only for one particle, for many particles. โอเคเราก็จะเรียนวิธีการที่จะแก้สมการการเคลื่อนที่ของนิวตันนะครับโดยใช้ระบบของเรานี่จะมีอยู่หลายพาร์ติเคิลนะครับเดี๋ยวผมเคยทำวิดีโอไว้เมื่อนานมาแล้วเดี๋ยวจะให้ดูว่ามันสามารถทำอะไรได้บ้างครับตรงนี้เดี๋ยวผมขอ copy link แป๊บหนึ่งนะครับ copy link over here so let's look at the video that will give you an example of what you will accomplish after studying this particular chapter. Okay, let me change the OBS scene to the Chrome and then change the window to the Chrome. So, okay, we have many things to show and that's why it takes a long time to switch back and forth. Paste over there. Okay, now you should see this thing here. This is the example of what we will be talking in this class. So we have many particles. These red dots here are particles in the system, and we are going to write a code to solve the motion of this particle under the influence of gravity, air resistance, and the Lennard-Jones potential. A lot of things in play here. As you can see here, you cannot solve this equation analytically นะครับเราไม่สามารถจะแก้สมการด้วยมือได้นะครับเพราะว่ามีแฟกเตอร์ต่างๆมากมายพอสมควรนะครับเราต้องใช้คอมพิวเตอร์ในการแก้สมการ So this video was made a long time ago, but the code and the PowerPoint that I had still there. It is all about the numerical method of how you can solve the motion of atoms and molecules. Okay, let's get back to the material in this class. I haven't gotten any questions so far. I've thought that maybe my internet connection has lost somehow. Maybe it's not, okay, because the class is very quiet. Let's go to the PowerPoint. presentation at the end, and there we have here. Okay, so that is about the last topic that we are going to be studying about here is called vector calculus. And but I can see the screen that the people are listening about the vector calculus. So we only have 2 weeks to cover this material, and I hope I have selected the most important 2 weeks of vector calculus. First is about gradient, divergent, and curl. The highlights, the topics, the climax that you are going to be studying here is about this meme. I've seen this meme on the internet. Is about how Newton's law of gravity and Coulomb's law of electricity are the same in terms of 1 over r squared. You know, you have these two identical relation between the distance, which is 1 over r squared. And why is that? Why is that? Is there something important behind this truth about this dependency? And also, one of the key questions is that why would the dependent be 1 over r squared, the r to the second power exactly, not 2.15, not 1.99 power, but 2 exactly. Okay, ก็เป็นหนึ่งในคอนเซปต์ที่เราสามารถเข้าใจได้นะครับว่าถ้าเกิดเราเรียนเรื่องของเวกเตอร์แคลคูลัสเนี่ยเราจะเข้าใจว่าทำไมกฎของนิวตันนะครับกับกฎของคูลอมเนี่ยมันแปรผัน1 ส่วน r กำลัง 2เหมือนกันนะครับแล้วก็ทำไมตัวเลขยกกำลังเนี่ยต้องเป็นเลข2เป๊ะๆนะครับแบบที่ไม่ใช่ 2.11 หรือว่า 1.99 เลข2เนี่ยมันมาจากไหนนะครับแล้วมันเกี่ยวข้องอะไรกับทฤษฎีบทของ gradient curl และก็ divergent นะครับ and also in this lecture about vector calculus I am trying to be as visual as possible. We will play a lot of visual effect about how we can see the field, the vector field in space. So I have this field play. It's called field play. Oh, okay. Let me go to this website that's called field play that allows you to see many of the mathematics in graphic. Okay. Let me switch back to the Chrome scene and then go to my Chrome website. There you go. There you go. So Control V to get the link. Now this, okay, this is a program by Ann Vaca, okay, and it allows you to see the visual effect of the math. For example, this is the field, the vector field in space. But after using this program, you can actually see it happens in motion. Like this, you have this flow of water going from left to right, okay? Or if you have this oscillating field, the first line go to the left, the next one to the right, but with visualization, you get this colorful concept. Okay, so we're going to use this very often so you have this understanding of what vector field is all about, and also looks pretty at the same time. Okay, so those are all the highlights and climax that we are that you are going to see in this 8 weeks of lecture. Let's see, let's go to Microsoft Teams scene and Microsoft Teams. Okay, so any questions so far before we begin the actual lecture on expansion, which is the first chapter of this class? Anyone? Seems very quiet and no question. Yes, Mrs. Dechen was going to say something. I saw it on screen.
Oh, I just want to say that the Ajah's explanation of the outline of lesson is very clear that we don't have any other questions.
โอเค โอเคโอเคเขาว่าอธิบายละเอียดเกินไปก็เลยไม่มีคำถามนะครับเดี๋ยวผมจะลองอธิบายแบบวางยาสักเล็กน้อยเพื่อจะมีคำถาม oh I'm sorry I have this here like an activity notice okay all right doesn't matter ลองทดสอบเสียงดังชัดเจนดูครับคุณณรวัตรคุณณราวัฒนวม okay so if you don't have any other questions again it's very childish for me to actually assign points on asking questions to the 3 students but we'll see how it goes ถ้าเกิดว่ามีคำถามน้อยอาจจะต้องมีการให้แต้มของนักเรียน3ท่านที่เรียนนะครับก็ถามเล่นถามสนุกสนานไปตามภาษาก็ได้นะครับ so without any questions then let me go to the first chapter in this class namely the expansion okay we need PowerPoint and so let's switch that and then go to PowerPoint presentation okay well let me close this window and then begin the expansion over here okay so let's begin the expansion okay expansion is a very important concept in mathematics. What is expansion? Expansion is an idea that a thing or an object can be broken into many pieces. For example, if I have a hand, this is my hand and it is an object, and I can break this hand into many pieces. For example, I would have fingers, which there are 5 of them. I may have nails, 5 nails. I may have also 1 palm over here. So an object can be broken into many pieces. And you also have the number, the coefficient that tells you how many of those pieces are there in the components. You have 5 fingers, 1 palm, and so forth. So that what expansion means. expansion หรือการกระจายนะครับเป็นคอนเซปต์ที่อธิบายว่าสิ่งใดๆสามารถจะแตกออกเป็นชิ้นๆเล็กๆได้นะครับแต่ละชิ้นเนี่ยก็จะมีคล้ายๆกับเป็นสัมประสิทธิ์เอาไว้คูณนะครับว่ามีทั้งหมดกี่ชิ้นนะครับ so let me look at the first example of the expansion for example we have an arrow the big green arrow here it can be expanded into many smaller arrows. We have 3 of the horizontal arrows, 3 over here, and we have 2 of the vertical small arrows over here. And this is what we write as the official notation. An arrow is called a vector in the mathematic terms, but I prefer to use the word arrow. It sounds, easy and informal. In addition to an arrow, we can also expand number ตัวเลขนะครับก็สามารถจะกระจายได้ให้เป็นชิ้นส่วนย่อยๆได้เช่นเดียวกันนะครับ so we can expand this number on the left hand side and makes it into many pieces and each piece are simple we have 1/3 and plus 1/5 and minus 1/7 and so forth. By the way, this is called Gregory series. So in addition to vector and number, you can also break a function into many pieces. Now this itself is very revolutionizing idea, very creative idea that you can do this. To see why it is creative, let's go to the iPad screen. Okay, นอกจากจะเป็นเวกเตอร์ตัวเลข นะครับเรายังสามารถที่จะกระจายฟังก์ชันนะครับให้แตกเป็นชิ้นเล็กๆได้เช่นเดียวกันนะครับซึ่งเป็นไอเดียที่ครีเอทีฟมากนะครับอยู่ในช่วงสมัยของปีประมาณ 1,700 เดี๋ยวเรามาดูว่าทำไมถึงมันถึงเป็นที่ถึงสามารถทำได้นะครับทำไมถึงต้องเป็นไอเดียที่มันครีเอทีฟลองมาดูในกระดาน iPad กันเสียก่อนนะครับ so we are switching to the iPad screen. Why is it here? Okay, so here is an example of why you can expand a function into many pieces. Okay, so let me first erase this here over my old board so far. Suppose we have a function, and to make it easy to see, I can draw my axis over here. This is my x-axis, and this function is e to the minus x, an exponential decay function. It looks like this. It always decay toward the right and keep decaying, getting smaller and smaller. That is my exponential decay function. On the left of the screen, I have an oscillating function. This like this one. Maybe this one is cosines of x. And also I have another sine wave that oscillates faster. Maybe this is cosines of 2x. I also have even faster oscillation like this. Maybe this one is cosines of 3x, for example. It is very surprising that we can add all of these waves here and here. Now notice how the wave always keep the same amplitude นะครับเวฟมันมี amplitude คงที่เสมอนะครับมันไม่เคยต่ำลงไปเลยนะครับคงที่เสมอแต่ว่ามันอาจจะมีความถี่ที่สั่นเร็วแล้วก็มากน้อยแล้วก็ช้าแตกต่างกัน
Professor.
Yes.
I would like to ask you about the concept of the expansion.
Wait. Okay. Okay. Now you may continue.
Yeah, thank you. I would like to know more about the concept of expansion, that it should be necessary or not that the expansion should be expand in the same axis, or it can be in the different axis system. Let me ask in Thai.
Do you mean the axis, the y-axis?
Yes, because of in the first example, you shown that you expand the vector like a projection to the axis. So and the waveform you expansion into the outer waveform addition, right? But it's the same axis system. But I would like to know that it can be in outer dimension or in outer axis system. It can be like that form, like a different.
Very good question. Let me go to the PowerPoint presentation and go back to this slide over here. Okay. The answer is yes. We can always expand the vector here into other direction. The way I define my x is horizontal, like this. So 3 horizontal. But I can also think of the x-axis this way. Here I am tilting my head, and I define my x this direction. Where is it? Oh, okay, yeah. This direction. Here, okay. This direction, and I can use this as my y or x direction as well. But usually, to prevent any confusion, we would put the prime or the dash next to the alphabet. Say A is 3 I prime and 2 J prime, like so. as long as you have the same number of dimension or the dimension is higher, you can always expand into any other choice of the x and the y axis. It does not matter. Okay.
นั่นหมาย
Very
ความ
good.
ว่า
I
เรา
hope
สามารถ
I answered. Yes.
นั่นหมายความว่าเราแตกเป็นอยู่ในแกนโพล่าก็ได้ถ้าเผื่อว่ามันมี meaningful เพียงพอถูกต้องใช่ไหมครับอาจารย์
I would say yes. I would say yes. I have seen. I know your questions. I would go with yes. Okay. คือเราสามารถจะแตกเป็นโพล่าก็ได้นะครับหรือว่าอย่างอื่นแต่ตัวโพล่าเนี่ยมันก็จะมีการนิยามแกน axis ที่มันเป็นตั้งฉากกันอยู่ปกติอยู่แล้วนะครับเราก็สามารถแตกได้เช่นกันนะครับถ้าเป็นระบบที่ดีโอเค so I hope I hope I answered your questions. Now where was I was in the iPad thing, okay, to show you that we can always expand the function. Okay, the iPad scene over here. Good. Okay. Now, it is very surprising that we can add many of the waves that I'm showing you here and get an equal sign over here. So this is equal. How could it be equal? คือมันจะเท่ากันได้ยังไงก็ในเมื่อด้านขวามือของสมการมันเป็นฟังก์ชันที่ต่อเนื่องไม่มีลดลงไปเลยนะครับแต่ว่าด้านซ้ายมือของสมการมันต่ำลงไปเรื่อยๆนะครับแต่มันก็ยังสามารถเท่ากันได้นะครับ so the way we do this is that we not only we add these wave on the right hand side we have to put the coefficient in front of each wave. Maybe we'll put 30% here. Maybe we'll put 10% of the high frequency wave, maybe another 5% of the high frequency wave, but somehow by adding this and by choosing the perfect coefficient, you get the exact function back. Okay, that is a very surprising concept that people had back then, maybe in the 17th century. Okay. So with this concept, let's go back to the example that I have. Okay, the PowerPoint here. Okay, all right. So in this animation, I am actually showing you the perfect coefficient that I was talking about. So if I add this sine and cosine graph, you know, the oscillating function with different frequency, you keep adding it. Maybe the first one you have 15.9% over here. The next one is 15.9%, still the same. The next one is 6% and so forth. And you can see that the two graphs become identical as we add more and more wave. We're adding more and more wave, 5, 6, 7, 8, 9, and 10. Okay, they become identical to each other, even though the shape of the graph are so different in the beginning. One is decaying exponentially, and the other is always oscillating with the same amplitude, but still you get an equal sign. And so that was possible. Another possible expansion is that not only we can expand this function in terms of waves, we can also expand them in terms of polynomial, you know, the n raised to the n power. In here, I'm showing you here is the animation. Oh, go back too fast. There you go. If you have this 1 minus x squared over 2, and so forth, the graph becomes more and more identical, and that's also an expansion. Okay, so we have a vector, a number, and a function. They can always be expanded into other function, other number, and other vectors. Okay, ฉะนั้นเพราะเรามี vector, number แล้วก็ฟังก์ชันซึ่งสามารถจะกระจายให้กลายเป็นตัวอื่นๆได้นะครับทีนี้ มาดูคำศัพท์ที่เราใช้เรียกกันก่อนเพื่อเวลาที่คุณจะไปอ่านหนังสือเพิ่มเติมจะได้ดูออกว่าเขากำลังพูดว่าอย่างไง so let's look at the terminology that is used in research and textbook. The functions that we are expanding into, we call that basis. Okay, basis, like the I hat and the J hat vectors, those are the basis. Or the cosine and the sine function, this is what we call basis. There are many type of bases depending on the shape or all the applications. If, for example, you have this oscillating basis, we call this a Fourier expansion. On the other hand, if we have this polynomial as a basis, we call that Taylor expansion. There's also a story that I heard. It should be a true story that actually Taylor and Fourier were I don't know who was the first one who invented this expansion, but one guy tell the other guy that their work is crap. Okay. ผมจำไม่ได้ว่าใครเป็นคนคิดคนแรกอาจจะเป็นเทเลอร์หรือว่าฟูเรียนะครับเขาคิดมาได้แล้วปั๊บเขาก็มีคนหนึ่งตามมานะครับแล้วก็คนแรกนะก็บอกว่างานของคนอีกคนหนึ่งเป็นงานที่ก๊อปปี้มานะครับเพราะว่าแค่เปลี่ยนเบสิสเฉยๆนะครับแค่นั้นเอง and so we have basis and we have two kinds of basis here. So the question that we are going to ask in this lecture is how do we find this magic coefficient? How do we find it? If we go back to the previous graph over here, you have this A number, and I choose this A to be these coefficient. You get this perfect match between the two graphs. But how do we find this? Okay, that's the question in this lecture. And to answer this question, we are not going to just give out the formula, but we are going to sort of derive and get the idea how you get that formula for the expansion and for the coefficient. But first, let's look at the application to get you excited about this material. Why is it useful? Okay, because and I believe one of the research that Miss Patrada is doing here is about quantum mechanics. And when you solve when you solve high-tech quantum simulation, you use what is called expansion. Okay, we'll see this material maybe in the third or the fourth week of the lecture, where you're gonna learn how to do the programming to solve Schrodinger equation. Okay, now even in engineering, we use expansion over here. So this is a technique that is called finite element. So we divide the entire area into small pieces, and we are going to find the solution of this problem only inside this triangle, that triangle, and those triangles. So we look at this, and expansion is used in this application as well. Okay, even this core simulations, the bone structure. This is the material for the fourth, maybe the fifth chapter of how we are going to use the expansion and numerical method to solve diffusion equation. Okay, without going into detail, if you focus on this here, this tiny equation here on the lower right corner of the page, you should see that we have this solution row. This row is the solution of the equation, but we can write that as an expansion. of the wave, the cosine wave. So if we figure out the coefficient an, we get the entire solution as well. Okay. So well, a thing as to sum up the thing we have talked about so far, a thing can be expanded into many things like vector, number, solution of an equations, and so forth. Okay. And I believe we will have time to talk about the Legendre polynomial expansion as well for this week's lecture. Okay. All right. And that is just over here. Well, I guess I have this already here. I think I should go slow over here. Okay. So we have this Taylor expansion. So let's get to for Taylor expansion, if you would focus here on the screen that I'm showing you, you should be able to see that quite clearly. We have this function f of x, which can be written as a summation of many polynomial. Let's say x to the n power, like so, okay? And we need to find the coefficient in front of this x. Like in the same way I have 5 fingers, who have 1 palm, I would have this mixture percentage an for this polynomial, and I sum them all up. I get this expression, okay, over here. So in this case, we are using the polynomial x to the n power as the basis of the expansion. But we don't need to. We can choose another basis. เราสามารถจะใช้ basis อื่นๆได้นะครับไม่จำเป็นต้องใช้เป็น x กำลัง n เสมอไปนะครับอาจจะเอา x กำลัง n เนี่ยมาบวกกันให้เป็นรูปร่างแปลกๆก็เป็นไปได้นะครับ so we can use other kinds of basis. One of the other kinds of basis is called Legendre polynomial, or in Thai they would pronounce it เลอจองอนุกรมเลอจองครับลักษณะแบบนี้ so what is it? What is Legendre polynomial? Okay, if you look at this PowerPoint presentation here, the P0, the zero order of the basis is number 1. Well, that's the same thing. It's the same thing as the Taylor expansion here for the zeroth order. x กำลัง n ก็เป็น0เหมือนกันนะครับเพราะนั้นเลอจองกับ Taylor ที่ order 0ก็จะเป็นอันเดียวกัน so if we go to higher order of Legendre polynomial, it's x. That's the same as the Taylor choice of basis. We have x to the 1 power, that's x. But starting from the second order here, they begin to be different. For example, in the Legendre polynomial, we have 1/2 3x squared minus 1 here. But for the Taylor, we only have just x squared for Taylor. So why do we do that? Why do we go into a lot of troubles making all of these complicated shape and function just to expand the thing? Why not just use Taylor as we have over here? Okay, and we are going to find that out in almost toward the end of this class. Okay, so in here I'm showing you the graph of this Legendre polynomial. Okay, we have this one constant, we have this linear function x, we have this parabola over here, like so and so forth. Okay, now I have this comparison. Okay, if we expand the same exponential decay function into Legendre polynomial, and I happen to find this perfect coefficient, I call that A0, A1, A2, the perfect mixture of that polynomial, I would get this graph. let us see. That is the comparison between these two graphs over here. The Taylor is perfect. Legendre also perfect. The original functions also, as it is over here. So we have many choices of basis เพราะฉะนั้นเราสามารถจะกระจายฟังก์ชันใดๆให้เป็นในรูปแบบของหลาย basis ได้นะครับไม่จำกัดที่จะเป็นแค่ Fourier แค่ Taylor เป็นเลอจองก็ได้นะครับถ้าคุณไปเปิดตำราคณิตศาสตร์ก็จะมีอีกหลายซีรีส์นะครับที่สามารถที่จะเอามาใช้งานได้นะครับคำถามก็คือเพราะอะไรนะครับ Why do we have so many basis expansion set? The answer is that in many applications require many properties of the basis. For example, if you want to study the wave motion, you would need the Fourier basis. ถ้าเราต้องการจะศึกษาระบบที่มันมีการเคลื่อนที่เป็นคลื่นนะครับเราก็ต้องใช้ Fourier นะครับเพราะว่าสมบัติทางคณิตศาสตร์มันเหมาะสำหรับงานนั้นมากกว่าถ้าเกิดเราใช้แอปพลิเคชันต่างออกไปก็จะต้องใช้ซีรีส์นั้นต่างออกไปนะครับเพื่อความง่ายในการแก้สมการ so we use many of the expansion for that for each job that we are analyzing. Okay, now let me show you the comparison between the Legendre and the Taylor expansion. What we have here on the left, on the right, is the error of the expansion in the vertical axis. แกนตั้งก็คือค่า error ณจุดต่างๆของการประมาณนะครับส่วนแกนนอนนี่ก็เป็นค่าของ x นะครับที่คำนวณนะครับ so you will see that for Taylor expansion the error is 0 at the origin but as you deviate farther and farther from the origin the error gets bigger and bigger but the Legendre polynomial expansion has almost constant error like this นะครับในส่วนของเรือนจองเนี่ยมันจะมี error ที่ค่อนข้างจะนิ่งนะครับแล้วก็เรียบส่วนในกรณีของ Taylor เนี่ยมันจะเป๊ะมากตรงกลางก็จริงแต่ว่าพอคุณเลื่อนออกมาจากตรงจุดตรงกลางปั๊บ error มันจะสูงขึ้นอย่างเร็วพอสมควรนะครับเพราะนั้นนี่คือตัวอย่างของการใช้งานว่าขึ้นอยู่กับแอปพลิเคชันที่เราต้องใช้ก็อาจจะมีการเลือกใช้ basis นั้นต่างๆกันนะครับ so that end the introduction of the expansion. Now we are going to get to the very serious mathematics of how exactly do we find this perfect formula for the A1, A2, and A3, and so forth. Because we are studying the mathematics, we need to know how to derive this so we can apply this concept to your research as well. เราก็ต้องพยายามที่จะเรียนเพื่อที่จะรู้ว่าที่มาของการคำนวณหาสัมประสิทธิ์มันมาได้ยังไงนะครับเพื่อจะได้ไปประยุกต์แล้วก็คิดต่อยอดในกรณีที่คุณต้องการที่จะมีเซตของการ expand ของคุณเองนะครับอาจจะเป็น Legendre expansion you have your own function to expand what do you do then how do you compute the coefficient so you need to know first how you derive this coefficient an okay yes. Again if you have any questions just let me know but I think now it's very quiet here let me check if you are still there how many people are actually with us in here let me go to the Microsoft Teams scene and see the number of people. In the beginning, I saw there were 12. Now we have 14. Okay, let me check how if I can keep the audience until the end of the lecture. Okay. Anyway, if you have something to do, then it's fine. You can always come back and look at the video afterward. Okay. Where was I? I was in the I was in the control rooms and PowerPoint here. Okay. And let me switch to the PowerPoint. Okay, how do we expand? Okay, well, let's say we want to do Taylor expansion. And of course, we want to write a function on the left-hand side as a combination of polynomial. How do we find the A, the coefficient, the perfect coefficient? So let's do that. Let's see, I have here on the screen the comparison between the actual function in blue over here, exponential decay, and the red function here is just a number one. So they look the same, at least at the origin over here. Okay, at 0, they are identical. But as you deviate from the origin, the error gets bigger. ถ้าคุณดูกราฟนี้คุณจะเห็นว่าฟังก์ชันที่เราต้องการที่จะกระจายเนี่ยหรือฟังก์ชันสีฟ้าเนี่ยนะครับมันจะโค้งแต่ถ้าเกิดเรามีแค่ตัวเลขตัวเดียวคือเลข1ปั๊บเนี่ยมันจะมีค่าเหมือนกันเฉพาะในส่วนตรงกลางแค่นั้นเองนะครับก็คือ same value ถ้าเกิดเราย้ายมาด้านขวาด้านซ้ายเนี่ยมันก็จะมีค่า error สูงขึ้นนะครับSo let's move to the next expansion function. I add minus x to the right-hand side. Now let's compare these two graphs. The curve in blue is still the same over here, but look at this red line here. Not only we have the same value at the origin, we also have the same slope over there, like this. ที่ในฟังก์ชัน1 ลบ x เนี่ยนะครับนอกจากมันจะมีค่าเท่ากันตรงกลางแล้วนะครับความชันของมันเนี่ยยังมีค่าเท่ากันอีกนะครับกับฟังก์ชันสีน้ำเงินนะครับที่เราเริ่มมี2อย่างที่มันเท่ากันแล้วนะครับก็คือค่าเท่ากันณจุดตรงกลางแล้วก็มีความชันเท่ากันนะครับ so we move to the next order. Suppose I have another function added to it on the right hand side. We have 1/2 x squared. Well, not only we have the same value, we have the same slope, we have the same curvature, the same curve, okay, like so. And so that is the idea of Taylor expansion, so that the value, the slope, the curvature of the right-hand side are identical to that of the left-hand side. So how do we do that? How do we compute the value, the slopes, the curvature, and so forth? Let's see. If you study calculus a little bit, you will see this here. This is my function, okay? The value is the zero derivative. This is a function. And if I substitute x equal to 0 into this function on the right-hand side, what do I get? Well, I get this. I get this goes away. This a1 goes away. A2 goes away because x is 0. Only the surviving term is the first term. So therefore, we have this equation that a0 is f0. Since we know what f is, we can just compute a0 using this equation. ทีนี้เราก็ลองแทน x เป็น0ใส่เข้าไปในฟังก์ชันของการกระจายก็จะพบว่าเราได้สมการในการหาค่า a0 แล้วนะก็คือค่า f ณจุด0นั่นเองนะครับ so we move to the next concept. The slope has to be the same. On the left hand side we take derivative, the first derivative, that's what the slope mean in calculus, f prime. On the right hand side we also take the first derivative as well. So what do we get? This goes away because it's a constant. A1x becomes a1. A2x squared, you take derivative, you get a2 2x and so forth. Now we substitute x0 into this polynomial, and what do we get? We get this equation of a1 is f prime at 0. Okay, so we keep moving on next into the order of this expansion. curvature in calculus means second derivative. So on the left-hand side, we have f double prime. Now, since we know what this is, we can always do the calculus to get f double prime. What about the right-hand side over here? Well, this one is a constant. You diff, it goes away. This one, we only have a2 times 2 left. Now this guy here that I'm pointing here, you take this power 2 downstairs, so we have 3 times 2x, okay? And so we go with the same process of substituting the x0 into this expression. What do we get? This goes away, and so a2 is f double prime. Now we have this denominator here เรามีส่วนนะครับส่วนตรงนี้เพราะว่ามันมาจากของการค่อยๆดิฟเป็นออเดอร์มาเรื่อยๆนะครับ so we have this denominator here that comes from how we differentiate the polynomial, and for higher order we have this an is equal to 1 over n factorial f to the nth power of the derivative. Okay, so that is the idea and the final formula of the perfect coefficient for polynomial expansion. That's how you do it. So to sum up the concept, you simply begin by writing down this equation here that I want to expand this function, anything, my hand or anything, into series of polynomial. How do I find the a coefficient? Well, we begin by say that the two sides of the equation should have the same value at the origin, same slope, same curvature, and all the order of the derivative. And that is the concept. And if you use that concept, you get this as the final formula for the expansion. The an is 1 over n factorial of df dx to the nth power of derivative. Okay. Now, a lot of slide. So let me slow down a little bit and show you exactly how we do the thing hands-on, okay, using my iPad over here. Okay, I don't know, let's do that. Find the coefficient of the Taylor expansion up to third order of the function e to the minus x. Okay, let's do that together. It's going to be very fast, but I guess that'll be a good exercise. So let me switch back to my iPad screen so I can draw it more beautifully to see how you do it. Let's see the control. My iPad screen is on the big screen, and there you go. Okay. So what is the problem that we are facing right now? So I want to expand this function f of x, and that makes it equal to huge expansion a0, a1x, a2x squared, and plus ... Okay, to the third order of the expansion. And you remember from the previous slide, I have this formula that an is equal to 1 over n factorial and derivative to the n order of the f, and then you substitute x equal to 0 into the derivative. Okay, and in this case, the function that we are having is the exponential decay function. So let's do it. So what to begin this here, I can just compute the f prime, okay, because I have the f on top. the derivative of the exponential decay function, if you know calculus, you get the same function back, like so. But you also have to take derivative of the exponent of this function. So when you do that, you get a coefficient of -1 in the front. Okay. So what do we do next? Okay, in this formula for the expansion, we have to substitute the x0 into the form of the derivative. So let's do that. Let's substitute the x0 here. So what do we get? We say x0 is equal to, you put 0 here, you get e to 0, which is a number 1, like so. What about the first derivative? You put x0 here, which is you're going to have the e to the 0 and then the -1 to -1 over there. Okay, so I can skip this process a little bit because you can do that at home. If you do the second derivative, you're gonna get the opposite sign, which is you have +1. And the third order of the derivative, you get back another -1 over here. Okay, so you have this alternating plus, minus, plus, and minus, and so forth. So we are going to use this information and put it back to this formula for the expansion. Okay, so let's do that. Let's do that very quickly. So we have equal, like so. The first order is number 1 because we have here is 1. The next one will be a1x. So what is my a1? It's -1 divided by 1 factorial, which is 1, and then x. Okay. The next order, what do we have? Is a2x squared. What is my a2? Well, a2 is +1 divided by 2 factorial, which is 2x squared. And the last one is -1 over 3 factorial. Okay, let's put it here. 3 factorial, which is 6. 3 times 2 is 6. So let me put the number 6 right there and x cubed over here. So we have these Taylor expansion already. Is it true? I don't know. Let's go check. We can check this answer with what we call Google collaboration. So let me take this opportunity to teach you or tell you something about Google collaborations, so you can use that to do your research or your programming as well. Okay, and we're going to use that to check this answer. So how do we do this Google collab or what is it? To show you, I need to change to my my web browser screen. Oh, I forgot to speak Thai. ลืมพูดภาษาไทย เป็นเพราะว่าบางทีผมสอนมันเกินไปก็ลืมพูดภาษาไทยนะครับไม่รู้ว่าที่พูดมาเมื่อกี้ฟังเข้าใจหรือเปล่า
เข้าใจค่ะ
Thank you. Okay. So see, I still have 14 people in this lecture. So let's go to ลองไปดูที่ Google Colab นะครับว่ามันคืออะไรเสียก่อนนะครับ Google Chrome. Okay. So ถ้ามีโอกาสมาดูที่ในเว็บของ resources ตรงนี้นะครับ look at this resources. You can click this first Google Colab file. Click on expansion. Now you would need first the account in Google or Gmail to do this calculation. Click on that. It will take you to this window, in the beginning. Okay, this window is the Google Colab platform. So what is it? This is a Python program that you can run on the website, and the program is going to be executed in Google's server somewhere in the US or whatever it is that they set it up, not in your machine. And you can see the output of the calculation. So when you come to this Google Colab, there are many windows, and the windows can be of two types. One is the text window, like this. You can show the text, the information, and so forth. And the last type will be the code shown in this play button here. Here is I'm showing you the code. And when you want to run the code, just click on this play button, and it's going to be computing what about the Python code that you are doing, and give you the output. In the beginning, it would take some time, but at the end, here we have this graph here. Let me magnify it bigger so you can see the code easier. Okay, I think it's too big there. Over here. Now, you don't need to know how to run Python code. You just need to change the code a little bit. So คุณไม่จำเป็นต้องรู้วิธีการเขียนโปรแกรม Python เพื่อที่จะเล่นกับตัวสคริปต์นี้ที่ผมเตรียมให้นะครับเพียงแต่รู้ว่าคำสั่งบางคำสั่งมันคืออะไรแล้วก็แก้เล็กๆน้อยๆตามประษานะครับ For example here in Python we define a function using def keyword, and here I am defining my f function like so, and this is my definition of the expansion. You see, they're the same. Well, within -1 and +1 range. If I change the range of the graph, let's make the range a little bit narrower, like this here, only from -1 to +1, and then you can just click play again like that, and you're going to get this graph almost perfect. Wow, look at that. Look at that. Now if you get a wrong expansion coefficient, let's say you miscalculated the coefficient, and somehow you forgot the sixth division instead. Okay, and then you click play, and you going to have this wrong graph. The graph will not be the same between the polynomial and the actual function that we are trying to explain. So we can use this code to actually verify many of the homework that you are going to be doing in this class. Okay. We have gone through an hour and 10 minutes for this. Anyway, am I speaking too fast? Anyone?
No, it's okay.
No? Okay. And I hope that, sometimes if I am too excited, I tend to speak faster a little bit. And I usually forgot to speak in Thai. What about the Miss Chanidapa here? You haven't asked any of the question, and I'm wondering if you're there.
Actually, I don't have it now.
Okay.
I'm right now.
Okay. Very good. I'm just checking with you. Okay. So this is that is the how you can do the Taylor expansion. I have other example over here that I have done on the homework problems, and let me show you this over here. So I hope you can see that clearly on the iPad mini screen over there. Suppose we want to expand another function, namely the square root of 1 plus x. What do we do? How do we find the perfect coefficient? Well, we can, in the beginning, make sure your exercises to make your workspace nicely. You can have a drink and so forth, like I have these chips. And then you begin to organize your notebooks and your board. I have this here, which I'm showing you here. I write this f of x, and then I substitute the 0 into this x. I guess I get 1, and then I begin to compute the first derivative f prime. I get something, and then I would substitute the 0 into f prime over here. I get 1/2, like so. I keep going into the order, second order, third order, and so forth. And at the end, I have this. This final function. So let me show you how to change the Google Colab file so we can check this expansion. Okay, here I didn't change my new definition of the function f. Let's make it okay. Okay. First, I need to back down a little bit. Okay. When you play with Google Colab, when you make the changes to this file, it will save the change automatically, which I don't want that, because I want to play around with it without having any, without saving the file. So to prevent automatic saving of the file, you can go to toolbox and command, and then look for playground. Where is it? Where's the playground? Where is the playground? Where is there? Open in playground mode. So what this means is that you can play around with all the changes without saving the actual file. Okay, so I open this in playground mode, and okay, now I just need to find the code. Okay, now I can make any changes without affecting the class material. So let's go back here. I would need to have the square root sqrt, that is the math function for the square root, and then 1 plus x, that's the definition. Okay, and then I just click play to see how we expand this. Is it successful? Is it a failure? Let's go back. Oh, the graph looks awfully wrong. Okay, why? What did I forget? I forget to change the coefficient, okay, of that expansion. The first one is x. The next one is actually plus 1/2 times x. The next one will be the minus 1/8 times x squared, like so. And I only have the 2 order of the expansion, and so I deleted the third one, and I played it again, and let's see if I get this right over here. Very good. Okay, very good. Now you start to see the behavior of the Taylor expansion. What is that behavior? If you are at the 0 over here, it is a perfect value. But as you deviate farther and farther from the origin, the error gets bigger and bigger. ถ้าคุณมาไกลจากจุดกำเนิดตรงนี้ error มันจะสูงขึ้นนะครับจนบางทีมันอาจจะเกินที่จะยอมรับได้ในแต่ละงานนะครับ so make sure that you understand your error tolerance before using this expansion. Okay, so I hope that you now able to access Google Colab and then play around with this a little bit. How you do that? Maybe I will have another. Yes.
Sorry, I have a question. I mean,
ถามเป็นไทยก็ได้ครับ
ถ้าสมมติผมแบบอยากให้ error แบบสมมุติเฉพาะส่วนที่แบบเกินสมมติไอ้อย่างนี้ของอาจารย์บอกว่าเป็น x เท่ากับ0ใช่ไหมฮะถ้าเกิดสมมติผมอยากให้แบบ error ที่ x เท่ากับ 0.5 มันเท่ากับ0แสดงว่าผมต้องแทน x เท่ากับ0เท่ากับ x เท่ากับ 0.5 ถูกไหมแทนที่ผมจะแทน x เท่ากับ0ผมแทน x เท่ากับ 0.5 แทนอย่างนี้ถูกไหมอาจารย์ตอนผมกระจาย
Okay, so the student is asking that suppose we want to make the perfect point not at 0 but at other points, say 0.5. So suppose you want to make that point here a perfect point. Instead, what do we do? Yes, you can do that. There is a way to change the center of the expansion from a 0 point to something else. Maybe you would choose to expand it around some other points, maybe around this point, around that point, and the center will always be perfect. Okay, we'll talk about that in the few slides from now. Okay, very good.
อาจารย์
Thank you. Yes.
อาจารย์ครับสำหรับในเรื่องของการที่จะคือ error มันจะเกิดมากขึ้นถ้าเผื่อเราออกห่างจากจุดศูนย์กลางทีนี้เนี่ยถ้าเผื่อเราอยากจะลด error ลงเนี่ยเราก็ต้องเพิ่มซีรีส์ให้มันยาวขึ้นคือเพิ่มเขาเรียกว่าไงนะเพิ่ม power ให้มันมีมากขึ้นแต่ว่าถ้าเผื่อว่า computing power เรามีน้อยจะมีวิธีอื่นไหมนอกจากเพิ่มซีรีส์ให้ยาวขึ้นนะครับในการลด error ที่ขอบปลายๆครับ
Okay, we change the basis. We can change the basis. We can change the basis, and the error will not be as much.
So we have two ways, right? That to decrease the error. The first one is to expand more series, introduce more series into the equation, and
Yes.
then we change the basis to order ones. That is
Yes.
the second. Okay.
Second, you can change to, for example, Legendre polynomial. If I would go back to the profile of the error for this Legendre polynomial, okay, this student was asking what can we do to make the error less? One of the things you can do is to increase the power of the expansion, or you can use other bases. Okay, let me go to the PowerPoint presentations which I have this comparison between the other what is it? Okay, once you gone here, what do we expand? There you go. We have this here, but I haven't choose my OBS. Okay, now you should see that I have so many control to worry about. There you go. Now here on the right graph, you see the error between the Taylor expansion and Legendre expansion. Even though the two expansion have the same order, which is the third order, but the error profile are different. For Taylor, you have perfect at the origin, but it gets very bad near the edges over here. But for Legendre, the error is not so good at the origin, not perfect at the origin, but they are the same roughly over the entire range of -1 to +1. And so, and that's how you need many other kinds of bases to do the job. Okay, this way.
นั่นหมายความว่าเรามีแค่2วิธีนี้หรือเปล่าครับที่ในการลด error ของการประมาณค่าครับหรือว่าเรามีวิธีอื่นอีกคือวิธีที่1ก็คือการเพิ่ม expansion มากขึ้นพจน์มากขึ้นวิธีที่2คือการเปลี่ยน basis อย่างเช่นการใช้ Legendre แล้วอันนี้คือ2วิธีพื้นฐานหรือว่ามันมีวิธีอื่นอีกซึ่งอะไรแบบนี้ครับ
Okay, so there are other way to do that which we will talked about in a very super fast way to do that. You can do this. Let me put that here on my iPad mini screen. See, okay. The third way of doing that is by iteration. Okay, and that will be the very good here. I get a chance to advertise my next lecture. We can do this. For example, we want to compute the square root of x. Now, what do we do that? And how do we do that in a very fast way? That's iteration. Also, we can use recursion, which we will not cover in this class. It's the way of doing. Let me show you an example instead of talking about that in the lecture. Recursion is one of the ways that is used very often in numerical method. For example, we can write a function f of x in terms of a square root of 1 plus square root of 1 plus square root of 1, something like this. So just keep going and going and going in order. So if you do it many times enough, you get almost perfect value back, like so. But we won't talk about this in the lecture, and we only talk about iteration in the next lecture. Okay, but I hope you can just use that keyword and put that in Google to learn more about the subject. Okay.
Thank you, Professor.
Where was I there? Okay, we're at the Google Colab over here, and the quick quiz. Very good. We at the quick quiz right now, and I hope that you by now have this working understanding of how you do the expansion and the origin of the formula for the Taylor expansion, which is you demand that the derivative, the value, and all the n derivative be the same for the function and the polynomial. So let's go to Fourier expansion. We only have an hour and a half left. Time's flying so fast. Okay. I think I have recorded the thing. Now we want to change the basis. We want something wavy. We want to change it to wave. But how do we find this perfect coefficient here? A1, A2, A3, and so forth. And here's how you do it. Suppose we ask, what is the A1 value? Now, certainly we cannot solve for A1. So, because on the right-hand side, there are so many things that are unknown. You don't know A0, you don't know A2, you don't know B1, B2, so you cannot solve for A1 alone because you have so many unknown variables in the right-hand side. So we need to figure out a way to eliminate all of the other, so need to kill A0, A2, and B, all the rest of the things, leaving only A1 survive. So how do we do that? เราจะค่าไอ้เทอมต่างๆอื่นๆทั้งหมดได้ยังไงเหลือให้เฉพาะเทอมเดียวเนี่ยมันเหลืออยู่เพื่อจะได้ย้ายโคไซน์เนี่ยมาทางฝั่งนี้จึงจะสามารถแก้สมการหา A1 ได้ Okay, how do we eliminate all the other terms on the right hand side? Well, what you can do, you can multiply cosine x on both sides of the equation, integrate. Why is that? Let's do that here. I multiply this red cosine x to the left-hand side and all the terms on the right-hand side, cosine x, and cosine x, and so forth. And then you integrate from 0 to 2 pi. Why do we integrate? Integrate ทำไมนะครับเพราะว่ามันมี because we have this identity of the cosine function and sine function. We call that orthogonal conditions. เงื่อนไขนี้เป็นเงื่อนไขทางคณิตศาสตร์ที่เรียกว่าเป็นการตั้งฉากกันนะครับตั้งฉากแบบคล้ายๆอย่างว่า we call this orthogonal because let me show you orthogonality in the vector. We have basis vector. This is my y-axis. This is my x-axis. Now, if you dot these two together, they get 0 because they are orthogonal. They're orthogonal. This is the basis, the y basis. This is the x basis. If you dot them, they become 0 because they're orthogonal. In the same fashion, you have this cosine of mx and nx as the basis. If you dot or multiply, integrate them, you get 0 if m and n are not the same. Okay, I can show you here. So why is that? So we have this condition that if m and n are not the same, you get 0. Which term becomes 0? This here is 0 because this one is cosine x and the other is 2x. They're gone. Here's is 1x and 3x. They're gone. They're all gone. On the first in the first term, you have cosine x and cosine 0x. They're also gone over here, leaving only this second term because you have this cosine square, double cosine. Cosine square is always positive, and it survived the cancellation. So what about the cosine and sine function? The same thing. If you have cosine mx and sine of anything, they become 0 because they are different bases. In the same way, you have this x and y, the dot product is 0. Or x, y, z, there are 0 permutation of the dot products, like so. So this condition is called orthogonality condition. Okay, in vector we dot them. In calculus we multiply and integrate them. Okay, so with that condition, the sine terms are gone, leaving only this term survive the cancellation, and now we can just move this integration here to the left hand side. You get this final answer, which is a1 is this top integration and the bottom integration so far. So that's how we kill the other terms. Okay, so I hope to make this lecture slow down a little bit. So I have this quick quiz just to show you step by step of how we can find the coefficient A2 from Fourier expansion. Okay, so I can use my iPad mini screen here to facilitate my derivations. On the left hand side, I have this E. It's too small. You might not see the text. Okay, let's make it big. E to the minus x. Okay, that is on the left hand side is equal to. So how do we kill all the other terms except A2? Any idea that you guys want to share? How do we do that?
I think multiply with cos 2x.
Oh, you multiply, very good. So simple, you just multiply cosine 2x on both sides of the equation. So when I do that on the left hand side, I have this times cosine 2x right here, and then I integrate from 0 to 2 pi, and then I should put dx over here. That's gone. Very good. On the right hand side, when you do that, you can use this orthogonal conditions, okay? And you see that when you multiply cosine 2x to it, this term goes away. This term goes away because this one is only 1x, but we are using the 2x over here, leaving only on the right-hand side the a2, okay? So let's do that. So the only surviving term on the right-hand side is the a2, which we can bring it out in front of the integration in my small mini screen iPad over here, and cosine square of 2x. Why square? Because we are multiplying the cosine 2x 2 times, okay? And that's how you you get this. That's how you get this formula for a2 is there integrations of the function that you are studying, cosine 2x, and then integration of cosine square of 2x dx. Okay, very simple. So I just put that in there just to make the things slow, not to go too fast with the presentation. Okay, so with that, summarize here, I can look at the mathematics book and look up the table of what that integral of the cosine square is and put that in the formula for my convenience. I get that. And I have this huge formula for the Fourier expansion. Okay, and it's just like that. Okay, very simple. Notice that we are multiplying that basis cosine nx to get the coefficient an. Multiply the basis sine nx to get the coefficient bn, and so forth. And that 1 over pi comes from the denominator of the equation right here. Okay, นี่ก็เป็นสูตรในการคำนวณหาสัมประสิทธิ์ในการแปลงฟูเรียร์นะครับที่เราใช้อยู่บ่อยๆครั้งซึ่งมันก็ได้มาจากการแก้สมการโดยการคูณฟังก์ชันเบสิสเข้าไปเพื่อให้เทอมอื่นๆมันตายหมดนะครับแล้วก็แก้สมการออกมาธรรมดานะครับการอินทิเกรตก็คือการ dot product ในเวกเตอร์นะครับก็มีคอนเซปต์คล้ายๆกันนะครับในเวกเตอร์เราใช้การ dot product ในฟังก์ชันเราใช้การคูณแล้วก็อินทิเกรตนะครับลักษณะแบบนี้ so I think let me show you how you find the coefficient an and a0 and bn for exponential decay function. Okay, how do we do that? Okay, so let's get to the example. Okay, to compute the integration, like here in my mini box here, we can use many tools. So welcome to the year 2021. So you might think that what is so important about this year 2021? Here I think is important. Okay, if you have seen this movie, okay, คนเหล็ก 2029. So this is the Terminator 2029. We only have 8 years left of normal civilization, and so things has been changed a lot lately. We don't have to do the integration by hand anymore, okay? Not anymore. So we can use a lot of free software, and one of the things that is free is Wolfram Alpha, which I can show you how to do that at this moment. So I'm going to find the coefficient A0 for the Fourier expansion. Okay, so how do we do that? You simply go to this website and then type in the code like so. It gives you this answer, 1.1752. What about the next expansion in the series, the first order, over there, right here? Okay, So it's very easy to do a lot of things in the Wolfram Alpha. So quick quiz. So let's do that and then plot a graph in the Google Colab platform. Okay. To go to Wolfram, let me show you this link over here. Where do I find here my let's go to this. For those that have not used this before, I recommend this. It's very easy. I do this all the time for my research, is to do that on Wolfram Alpha. Let's go to my Google Chrome. Let's go to my, where is my Google Chrome? Okay, that's my Chrome. And the window is too small. I can't even see. Okay, a PowerPoint should be, what about if I move this over here? Okay, now I can see the PowerPoint is too small. Okay, I can't see the PowerPoint. Exponential functions. So let's do the Wolfram Alpha, Chrome, so forth. Now we add the Google. So what's that? So how we do that? You go to Wolfram Alpha integrate from Google, and you can look at this example that they have. And I magnify the screen a lot big here, and you just type in an equal sign over here. Okay, this is an example. But for the A0, so what is the formula for A0? You have this function, exponential decay function, okay, and times from 0 to 2 pi. And then hit enter. It gives you that's the answer. And you have to divide that by a factor of 2, I believe. Maybe I forgot. I always forget this in front, and I can't even see that on the PowerPoint. 1 over 2 pi, that's right. 1 over 2 pi, and then integrate that. Okay. And you get that, 0.1588. That's perfect coefficient for A0. What about for A1? You simply multiply cosine of x in there, but I believe the coefficient in the front may be only 1 over pi from that formula, and you integrate again, and you do this, and you get that function, 1.588. So you do all this, and you put this number into the Google Colab over here. Okay, here is the second part of the Google Colab file, the Fourier series. Okay, notice that in this Google Colab file, you can also write the equation here too in LaTeX platform, in LaTeX language. I have here, and I have this equation here. So this, I define my function fx, and I define my Fourier function. I set the coefficient A0, A1, A2, A3, and so forth. And then this is my B, 0, 1, 2, 3. And I simply just put there into huge expansion. You see there, maybe if I can increase the screen, make it bigger. There, A0 cosine 0x, A1 cosine 1x, and so forth. And you just put in there, and I plot a graph. Let's plot the graph, see what happens. And you should see there you go, that's the graph. Okay, not so bad, not so bad at all. Well, because the order of the expansion is only to the 4th order, so it's not that good really. But you You can do that over here. Okay. So you can change this here to Legendre. Oh, that's okay. That's the next topic. Okay. So let's go to the applications. Okay. So we can have fun. We have been very academic for so long with this, almost 2 hours, and I'm afraid that you're gonna get sleepy. Let's go to a PowerPoint screen, see what we can do with the applications of this here. Okay, because I promised I love music applications of this lecture. Go to PowerPoint, and then I have this PowerPoint screen. Okay, we have this quick quiz, but let's skip that for now. Okay, quick quiz. Let's go to there you go. There you go. Where is it? There. Okay, let's get, before we have fun, let's talk about philosophical question. Okay, so we can have this interaction between this here, between the students. If I am looking at this graph over here that my mouse is pointing, you know, it looks like it keeps decaying from number 1. It becomes smaller and smaller and smaller. So, and I ask, what is this graph? And I have 3 choices for you to answer. Is it an exponential decay function? What is this function? Is it a polynomial? Is it a bunch of waves? Is it a group of waves? So what is it, this graph here? Any idea? Maybe Miss Chanidapa can share some thoughts about this idea in Thai or English is fine. So which one is it?
คิดว่าเป็น exponential decay ค่ะ
Okay, so she chooses exponential decay function. Okay, but with that choice, I disagree. I disagree that it's exponential decay function. Maybe, just maybe, can it be polynomial? Why? See, if I keep increasing this order of this here big enough, the graph become identical to perfect. So polynomial also give you this perfect graph too. What else? So now we have this confusion. It can be exponential decay, or if you have this huge polynomial to a large degree of expansion, you get the same graph. So it can be a bunch of power series. Can it be wave? What do you think? Suppose Miss Patarada think it's a wave. What would be the reason to think it is a bunch of group of waves? What do you think? Can it be a group of waves?
I think Palada is going to restroom right now. She texts me.
Okay, very good. Anybody
Okay,
else?
She back right now.
กลับมาแล้ว
Is she back? Are you back?
ค่ะกลับมาแล้ว
Are you back from the dream? Is it from the
แม่เราแอบไปนิดหน่อย แต่ว่าคำถามคือมันจะเป็นข้อ 4 ได้ไหมใช่ไหมคะ
Yes. Yes.
เนี่ย
That's
ผ
the
ม
question.
เพิ่งกลับมา
If I choose the C answer, what would be the reason for choosing the C answer? Can it be this graph here that I'm pointing? Can it be a group of waves? And why? Why is it? In the polynomial, I argue that it can be polynomial because if we increase the number of expansion to a very large degree, you get the exact same graph เราเลือกให้เป็นพหุนามก็ได้เพราะว่าถ้าเรากระจายขึ้นไปเป็นออเดอร์สูงๆมันก็ได้กราฟเดียวกันแบบ perfect เพราะฉะนั้นเนี่ยเราอาจจะมองได้ว่ามันเป็นพหุนามก็ได้หรือจะมองได้ไหมว่ามันเป็นคลื่นกลุ่มหนึ่งได้หรือเปล่าเลย
เอาว่ามันจะคิดแค่ช่วงใช่ไหมคะหนูว่าได้แต่ว่าคิดแค่บางช่วง
so if we focus only in a very narrow range of the function I have this animation to show you here there you go if I expand this graph into very high order of the wave you get the exact same agreement between the red and the blue. And so this graph here can be thought of as a bunch of or a group of waves as well. Now this wave has to have this mixture of the coefficient like so. You have to have 15% of this and so forth. So maybe if I look at this graph in a philosophical question มองในแง่ทางปรัชญา it's not about A or B or C but they all the same they all the same function the same truth just different representation โอเคมันเป็นฟังก์ชันเดียวกันทั้งหมดแต่ว่ามันเผยโฉมออกมาเป็นรูปแบบทางคณิตศาสตร์ที่ต่างกันเฉยๆนะครับเราเรียกอันนี้ว่าเป็นต่างกันของ representation เฉยๆครับ so they are the same function just different representation okay so we have so I have this analogy เราสามารถเปรียบเปรยได้ว่า so you know this picture they can have many format you can think of it as a JPEG format or GIF or BMP they are the same picture just different format you can have a book in paper or an ebook you can have this Iron Man or Tony Stark they are the same person just different representation so I hope you get this idea of the meaning of representation that we use very often in physics and in mathematics okay
so do you mean that in the different representation they have different characteristics they have different in the error characteristics something like that
that's right in different representations you have many characteristics in terms of mathematics but if you add them together they become as a sum the same function okay so I have these samples here of the real space representation and Fourier space representation in real space so what do I mean by real space in real space we mean that the variable is x the function is the functions of the x is 0 x is 1 2 3 and so forth so we concern ourselves with various positions like so this is real space real means the actual space you know the x and the y and the z but in Fourier space on the other hand we look at the mixture percentage of each wave for example with the n0 the zero wave without oscillation you have this a equal to 0.195 if you have n is one wave you know a somewhat faster wave you have this mixture of 0.19 you have this faster wave the mixture become 0.064 and so forth so we concern ourselves not with the position but with various frequency instead but remember they're the same function just different representation okay so the way in which we can convert back and forth between these two things in the same way we can convert JPEG to BMP, from JPEG to GIF, we have the way to convert real space information to Fourier space information that is called Fourier transform using this formula that we have just derived. That's very amazing. Okay, you have listened to this lecture for almost 2 hours now, and you know how to derive this transform from real space to Fourier space. Okay, now let's have some fun finally. Okay, let's see. We use a lot of Fourier space in music and in the wave study of wave and so forth. This is the Fourier space. Okay, we look at the percentage mixture at various frequencies with the wave 0, the wave number 1, different frequencies. How much of the mixture do we have in this graph? That is Fourier space. I can plot a graph. I can use this information here on the left and plot a graph here on the axis. On this horizontal axis, we have these frequencies. On the vertical, we have the mixture percentage or the intensity, 0.15, 0.15, 0.06, 0.06, and so forth. Okay, that's how we plot the graph in Fourier space. Frequency versus intensity in the vertical axis. Okay, now I want to show you this software that we can use to see in real time the comparison between the real space, or in this case real time, and Fourier time transform. Let me get to the screen so I can show you this nice graph over here. This is called frequency analyzer. Okay, I move this over here, move this over there, and move this over there, and I can change it to my desktop scene over here. Okay, I hope you're seeing this in real time. On the bar, the big window on top, that is real space representation, or in this case, time, real time representation. Okay, so as I'm speaking, the signal goes up and down, up and down. That is the real time or real space, real time representation. The box here in the lower left corner, you have a Fourier spectrum. Okay, now you cannot see easily with this because I am talking here. There are so many frequencies coming from my mouth. So let me choose the frequency by using this music instrument over here. So you see a very pure tone. Okay, for example, like so. Okay, I hope you see this increasing in the height of this Fourier space over here. As I go up into the note, you get this Fourier space representation or Fourier time, like so. Let me try that one more time. Okay, so that is, I hope you see this better in the video in the analyzer, but we are almost at, we have 1 hour left, and I think we should take a break a little bit so we can go to the restroom and so forth. Let's take a break for 10 minutes and we'll come back at let's say come back at 3:05. Okay, 3:05. So a little bit, and I hope that you have. Let me see how many people I have left in this present. 13. Okay, I'm doing very good in this presentation. Let's see. I need to show you that the time that we will come back. The Microsoft team. Okay, and then we'll come back at 3:05. Okay, 15:05. I'll be back. That's Arnold Schwarzenegger's. I'll be back at 15:05. Okay, give me a little bit of a coffee time and so forth. Okay, I'll see you then. Let me put music on a little bit. So we still have a couple minutes left. Let's see. Let's have this little talk with my cute students. So พัทรดาคุณฟังพอเข้าใจไหม
เข้าใจค่ะ
Okay. Where's music? I just stop music first. Okay. I hope you can see this on the screen. Let's see. What I want to show you here also has to do with the Fourier expansion. Usually, the metallic instrument, เครื่องเล่นที่มันทำมาจากโลหะนะครับ it has a very pure sound, but when you have this guitar or string instrument, the sound is not pure. Let me show you the analyzer in a moment. Let me go back to this screen, desktop screen. Okay. Show you here the sound for the metallic is very pure, and if I put this note, you see this sharp line. So you can use this as a signature to analyze what kind of instrument we are playing. See if I can play this. What about the guitar? Okay, I'm going over here. The guitar sound is much like this. There you go. So as long as we are on the guitar, I might as well take this as an opportunity to, practice my art. Now let's pause the science a little bit and worry about the art instead. You can look at the real space Fourier for the top window and the Fourier space here. Okay, in this lower left window. So which one you want to hear my tune a little bit? In English though, when I was young, I listened to the radio, listened to my favorite song. When they play, I sing along. It made me smile. Those were the happy times not so long ago. Oh, I wonder where they've gone. But they're back again, just like a long lost friend. Oh, the song I love so well. Every sha-la-la-la, every woe-woe-woe's to shine. Yesterday's once more. I don't hear any applause. Let me give myself an applause. Okay. So I hope you have you relax a little bit about the Fourier expansion. The lecture wouldn't be complete without the Thai, because I need to switch back and forth between English and Thai. Let's see what Thai music do I know how to play and sing. I guess I only know the older version of the musician, Sek Lo So. ตั้งแต่รู้ว่าเธอต้องการจากไปหัวใจฉันเริ่มอ่อนแรงตั้งแต่รู้ว่าใจของเธอเปลี่ยนแปลงเรี่ยวแรงของฉันไม่มี ใจฉันมีความสุขเธอคือทุกอย่างที่ฉันมีสิ่งที่เธอให้มาเป็นสิ่งที่แสนดีแต่มาวันนี้เธอต้องการไปเธอบอกว่าฉันไม่ดีมาบอกตอนนี้มันสายไปก็ตอนที่ฉันรักเธอแค่ครึ่งใจI forgot how to play it but you get the idea of the real space and Fourier space expansion. Now let's get I have this note from someone but I could not see what happens. Oh, okay. There's a plot here. Thank you very much. So let's get back to the difficult subject of Fourier expansion and switch to control PowerPoint and then I need to because it's gonna crash. Let me turn off this software. Okay, very good. Okay, now we have the that's another. So the application, what can we do now that we understand the concept of Fourier space and real space? What I do all the time when I sing karaoke song is that I would use this software to shift the tone, the pitch of the music, because sometimes the music is too high of the tone. I cannot reach, my voice cannot reach that tone. So I would use the software called Audacity to lower the pitch a little bit so I can sing that song and then save my file so I can sing later on. The second application of this Fourier space is what you can do with autofocus of a camera. So I don't know. Let's make it a homework problem to think about. Think about that. How can you use the concept of Fourier expansion to implement autofocus of an image? Okay, let's see if you can do that. The third application of this Fourier expansion is weather satellite image signal. Let's talk about that. So we have this satellite called NOAA-15. And it always circles the Earth 2 times a day with this satellite, and take images of the Earth below, so you can see the clouds, the storms, and so forth, and send the signal of the image data down to the ground. Now I had experience of receiving this signal when I was maybe in undergraduate, and I can decode the signals, and let's see how the signal is encoded. This is the image of that satellite, this picture, and if you can see this, if you can hear the signal of this satellite, you will notice how we can use that Fourier expansion to send the signal from space to the ground. Okay, I have this YouTube video. Let me copy the link from here. Where is it? There you go. As the link. Where's the link? Okay, that's the link, and I can copy this link and put that in my Google Chrome website, web screen. Let's change that to Chrome scene, and then it'll be nice to have this close. Okay, now put it there, Control V. Okay. So this is the actual signal that you can hear using the FM receiver from the satellite. I believe that the frequency that is transmitting is 160 37 megahertz in the FM frequency. If you hear that sound, the sound looks like this, what you're hearing now, ding, 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 ding. But if you put that sound into analyzer, you see this spectrum of Fourier spectrum, and that is the signal from the satellite. You can decode the signals and convert that to the image that you see previously, okay? And that's how you encode the data stream using Fourier expansion. Actually, I believe there are, if you know fax machine, does anybody know fax machine or an old days modem? If you have experience listening to the modem when I was young, when I was a teenager, the modem would sound like this, like in the Matrix movie, like this. Okay, that's how the modem sounds, and that is precisely how they encode the signals into the sound using Fourier expansion. Okay, so I hope you have something to go on with this application of the Fourier expansion and so forth. Okay, let's go back to the last expansion that we are going to study today, which is the Legendre expansion. Okay, I'll move this over here, and PowerPoint presentation screen and Microsoft PowerPoint. Okay, now, so to sum up as a review ที่เราพูดมาที่เราพูดมาทั้งหมดนี้นะครับ we talked about how we expand. We expand this in terms of the polynomial basis. We call that Taylor expansion, and that's how you compute the coefficient. Or we can choose the wave as a basis, that's Fourier expansion. Let's look at the limit of the expansion. Okay, now for the Fourier expansion, as you suspected, the range of the expansion only cover from 0 to 2 pi. It's like an angle. An angle only cover from 0 degree to 360 degree. In the same way that the wave can only go from 0 to 2 pi in radian unit. See, if I plot the graph and make the range bigger, like in the animation on the screen, you will see that the exponential function repeats itself. You know, it keeps coming back. So that's the limit of expansion. But there is a way that you can extend the range of the expansion from 0 to 2 pi to make it bigger and bigger to infinity. You can do that, but the details is not that difficult. Okay, I'll leave that to your homework for the reading assignment, how you would expand the range to any arbitrary L or any range of the expansion. Okay, เราสามารถที่จะขยายผลของการกระจายให้มันเกิน2 พายได้นะครับแต่นั่นเป็นเอาไว้อ่านเพิ่มเติมในเครสิกนะครับถ้าเกิดมีคำถามก็มาถามได้นะครับในคาบต่อไปโอเค Now the limitation of Taylor expansion, okay, that's very obvious here. Suppose I want to expand the Taylor series up only to the second order over here, and that is my function, a polynomial. So what happens is this: if the x is between or less than -1, the accuracy is very good. Why? You see, if x is small, when you square it, it becomes smaller, 0.01. When you cube it, it becomes even smaller. So the higher order is very small. Then you can just neglect, you can forget all of this higher term without losing any accuracy. Because as you go higher, the term becomes smaller and smaller, become insignificant. Okay. On the contrary, on the other hand, if x is bigger than 1, maybe right here, 2 or 3 or 4 or 5, when you square 10, it becomes 100. Cube, it becomes 1,000. That means if you go higher order, it becomes bigger and bigger, and you cannot neglect, you cannot forget the other higher term. That means it's going to be a very bad approximation when you have x is bigger than 1. Okay, and now there is a way to change the center. The center of the expansion can be changed from 0 to some other point, say number 2, in which case the number 2 will be the best approximation and the rest will be get worse and worse and so forth. Now you can look at the textbook of how you will find the formula for the expansion without the center, but I can show you here very easy. I can just give you the formula here. If you want to expand the Taylor expansion for some other center, let's say the center around x0, okay, in my mini screen here, x0 can be number 0, can be number 1, and so forth. The formula for coefficient an is equal to 1 over n factorial, like before, and then here's this, the derivative to the n power, like before, of the f, but then you substitute the x equal to x0 instead over here. That's the coefficient. And the function that you are writing down previously, we have this a0, a1x, and a2x squared. That's previous with the center at 0. But now we change it to some other center. We have this instead, a0 plus a1, and then x minus x0 to the first order, plus a2, x minus x0 to the second order, and keep adding again and again. Okay, now we change the form to make it more general, like so. Okay, so I will leave that to your curiosity to read more on the Krasik textbook. Okay, so to sum this up a little bit, so we move on to the next expansion in the list and the final material for this lecture, namely the Legendre polynomial. Okay, these polynomial, we call that orthogonal polynomial or orthogonal basis. Why? Because when you pick any two bases, they are always orthogonal. For example, you have this x and y and z axis as the basis. X is orthogonal to y is orthogonal to the z axis. In the same way that the cosine and the sine and the cosine 2x, they're all orthogonal. So the use of orthogonal basis is very important in physics and mathematics. One of that is Legendre polynomial, okay, like this. Now we have, instead of x to the n power, we have this function called b0x instead. Let's make it more general. So how do we, let's look at orthogonal basis, okay? Now I said that cosine and sine are orthogonal. Why? Because if you multiply them and integrate, they become 0 if the bases are different. If m and n's are not the same, you get 0. You get 0. That's what orthogonal means. Okay. What about the Taylor expansion? The polynomial n raised to the n power, x to the n power. They're not orthogonal, okay? Not in this topic. Why? Because if you multiply x to the first power and to the second power, integrate them, they're not 0. What about this? X squared and x cubed. Multiply them, integrate, it's not 0. So it's not orthogonal in this case, not applicable for this topic. The one that is orthogonal, which will be very sorry, which will be very convenient for the mathematics. Oh, I've lost the place where I've my hand is not as good as it used to be. Where is it? There you go. I'm sorry about the interruption. Okay, where was I? Okay, these are the set of orthogonal bases. It looks like polynomial, but it's not, because you have this mixture of x squared and 1 here for P2. You have this x cubed and 3x here for P3. So it's a mixture of all the polynomial as to make it orthogonal. For example, right here, the integration for this Legendre polynomial is by definition, this is by definition, by design, from -1 to 1, okay? Not some other range, but this one. So every polynomial will have its own choice of integration range. Maybe Miss Chanida Park can think of her own polynomial or her own basis to use, and she's going to have to specify her own range of integration to something else. Okay, so but for the Legendre polynomial, you have from -1 to +1. And as an example, you can show, but I'm not sure if I have enough time to show this. At least you can do this at home. If you take, by any chance, if you take P2, this polynomial, multiply that with P3 here, it's going to be a big expression, integrate that from -1 to 1, you will get 0. Just like magic, you will get 0. So that's how this Legendre set of polynomial is important, because you have this nice property of orthogonality. Okay, so you can learn more about this. Usually for very hands-on class in math methods, we will study this. We call this a special function, but you can look at online. Every function has its own properties, and you can learn how to use that maybe from Wolfram method, Math World. I prefer the Wikipedia as the initial source of information, but you always have to verify that. You know, this is the list of the polynomial. You can go up to almost any order you want, but usually in the real research, they would only go to maybe second or third order of the Legendre polynomial. That is the shape of the polynomial. Again, it's only defined within the range of -1 to 1 only. So if your applications concern something outside this range, you're not in the good luck. Okay, so anyway, I can show you the me here. Skip real fast. I'm sorry, I don't have much time on the in the lecture, but I can imagine that that you can do this at home. Okay, I have this quick quiz over here. Okay, and this will be very good quiz to use the Google Colab. The quiz is the following. Suppose I look at this properties in Wikipedia, and in this Wikipedia it says when you integrate Pm and Pn together, you get this 2 divided by 2n plus 1. Okay. Yeah, okay. So I wanted to check, what if I have this P3? What if I have P3? Do I get the same answer as what Wikipedia says, like this? And you always have to do this in your professional scientist career, because I have the reason for this. Okay, so when you are a scientist like me, there's no teacher that give you the answer key. I mean, you are your own teacher, and you always have to check the answer if you get the right answer, because as Richard Feynman said that you can always get the wrong answer. You can be fooled by some information by yourself. So you always have to check. So let's check this if the P3 is correct by using Google Colab platform. Okay, this will be a good chance for you to see more of the functionality for the Google Collaborations platform. Let me go to the web browser control. That's my desktop Chrome scene, and then the Chrome here. Turn off this screen here, and there you go. This is my Legendre polynomial over here. There you go. Okay. Analysis. Let's look here. Is the Google Colab for, I have here, I defined my function once again in Python, the function that I want to study, exponential decay function. I then define my Legendre polynomial, which I copied from the Wikipedia. You see, I have P0, I have P1, P2, and P3, and so forth. Now, in this Python code here, I can use this code to integrate using the computer integration and get the answer. This is how you do it. You have to define a function called integrand, which I define as P0 times P0, but I can change that to P3 to show my answer, P3 there, P3 there, over there, and I just, click run like so, and I check the answer. The norm, or the integration in this case, is 0.2851, and you can always check that with the Wikipedia's formula. What was that? If anybody remember the formula, so I can check that in my Google. What was the formula for integration of P3? What was that? Anybody? I believe it was the 2 divided by 2n plus 1. 2n plus 1 is 2 times 3 plus 1 over there. Enter. 0.2857. Very good. So if I go back to my Google Colab, I get the exact answer over here. Okay, so this is one of the command you can use to integrate any function that you defined using Python and the Google Colab. Okay, maybe I'll have this special tutorial session of how to use Python in science and in mathematics later on. Depend if you want, just send me a signal that I will consider having a special lecture on that. Anyway, let's go back to the concept of expand this in Legendre polynomial with orthogonal basis set. What do? I need to go back to my PowerPoint, and then PowerPoint Windows over here. Okay. Now, I have another story here to tell you. I have many stories. Maybe I'll skip this story because the time is not permitted. I'll talk about this story next class if we have time. Okay. So how do we expand it? We want to expand this function f of x in terms of a0, b0, and a1, b1, and how do we find this magic coefficient an? Any idea? Let's wait for the idea. So and we know in the beginning that all of these bases are orthogonal. It means if you multiply by something else and integrate it, you get 0. So any idea of figuring out the perfect coefficient an, any an? Let's ask Mr. Pattarada. Yes? I can. Am I? So it's all quiet.
อะไรนะคะ
Okay, I thought my internet has gone bad. So how do we compute an in this case? Any idea? I write down this function f of x on the left hand side, and we have these expansion, many terms, b0, b1, b2, and so forth. How do we find the coefficient an using these properties of orthogonality? It's okay, I can give you some time to think about that. No, it's clocking. I have this. Why can't I play it? It's all weird. So, are you still with me?
คูณ bm อะค่ะ แล้วก็ตัด
Yes. Very good. So if we multiply by other function bm that is not n, you see, if I do that, multiply bn and integrate, then all the other term will be gone. You see there, this is bn, b0 becomes 0, and the other one is 0 and 0 and 0. So we only have this term left, because this is the only one with n and n, the same n. Then we can just move this and divide that to the left-hand side, and we get this formula for the expansion an, okay? And I can't, well, let's see, there's something wrong with my my PowerPoint. Seem to let's see if I can. Okay, I have to switch back to my PowerPoint and then
ไม่
switch
กลับ
to
มาค่ะ
the screen. Okay. I think I'm back now with the oh man, there's something wrong with the selection. Okay. I don't know what happens, but the computer seems weird at the moment, and I cannot show you the rest of it. I'll be lucky if I can. What happens if I show? Okay, it asked me this. Okay. I can't put the window in other mode. Okay, and let me turn off the PowerPoint and then open it again to see if the problem goes away. Expansion. Oh, here. Let's see, PowerPoint. There you go. My window is coming online, and we have this. Almost died. Okay. Oh, I can't. If I show this, it seems though that something is. Okay. Man, this is very bad. Look at the time. what do we have right now? So I guess the system has gone wrong, and I cannot recover it easily. Maybe it's good time to stop. It's gone too long. Okay. Let me go back to the. Let me pause this lecture here a little bit and go back to the Microsoft Teams window so I can see my students and the audience better. Somehow the system has crashed, and I think it's good for me to stop right here. Okay. So we'll continue this lecture next week with the Legendre expansion. I recorded this here already, so you can always come back and see, or you can ask questions online in this Microsoft Teams. So any comment that you so far that you want me to change or improve or customize the things for you for the next week presentation, which will cover the Legendre expansion and how to find the coefficient, but you should get the idea already of how we can do that. Any comments so far? Am I speaking too fast? พูดภาษาอังกฤษพอเข้าใจไหม or some other things. Any comments you want to share?
นี่ก่อนเลยค่ะ
Yes.
I think the portion of the screen is quite small for the presentation and for the iPad screen. And for the coding, I think you may expand the size of the portion of the coding that may be better for looking into the code.
Okay, what I got is the screen is too small, and what was the next part about the code?
น่าจะเป็นเพราะว่าเนื่องจากว่าหน้าจอมันมีส่วนของโค้ดที่เล็กเกินไปเวลาขยายมันเลยเห็นโค้ดน้อยครับอาจารย์อาจจะแบบว่า
มันเห็นโค้ดไม่เต็มจอคือส่วนของโค้ดที่เห็นมันมีบรรทัดน้อยเกินไป
ใช่ครับอาจารย์
Okay. Good. Okay. Thank you. So I am going to adjust the presentation accordingly. I have many Thai audience. We have this 15 people now. How am I doing with the English presentation?
โอเคค่ะฟังรู้เรื่องได้เลยค่ะ
Miss Chadapa says it's okay. I thought it was great.
Yes,
I was hoping you would say great, but you said okay. Okay, that's good.
ที่เขาบอกเรื่องสไลด์อะค่ะทีนี้เหมือนว่าสไลด์ตรงที่เป็นหน้าโค้ดหรือว่าหน้าอื่นก็ปกติค่ะแต่ว่าสไลด์ PPT มันเล็กใช่ไหมคะทีนี้หนูก็สามารถซูมได้จากฝั่งหนูแต่ว่าพอซูมไปแล้วอะค่ะน่าจะเป็นเพราะว่ารูปอาจารย์มันแตกอะค่ะพอซูมไปมันก็เลยยังมองไม่เห็นอยู่ดีอะค่ะ
Okay. So
แล้วก็เมื่อกี้อ้อมบอกว่าช่วงหลังเร็วมากเลย
Okay, very good. Thank you. So it's too fast with the Legendre polynomial, I guess. We'll have time to come back and yes.
อาจารย์จะให้ PowerPoint ไหมครับ
ครับผมเมื่อกี้ว่าอย่างไงนะครับ
อาจารย์จะให้ PowerPoint ไหมครับ
DSK? Oh, okay. I'm not sure about the PowerPoint presentation because you already get the video. And since I'm not the only sole author of it, let me talk about that with my colleagues first. Maybe we'll talk. I'll tell you next week, okay? Because I want you to actually take notes of the video of the. But it's a good point to raise. Thank you. Any other comments? Okay. So I guess we are almost out of time, and I'll see you next week. I hope you have fun with the code and the things here. Okay. Thank you. I'll see
Thank
you
so
next
much,
week.
Ajahn. Thank you, Ajahn.